Welcome to Brain Vision.
Okay, so here we have about 10 Lewis structures that we have to draw for all these compounds. So let's start with the general rules of Lewis structures. First, you always want to count up all your valence electrons. So you do that by looking at the periodic table and determining how many valence electrons each atom has in the molecule. And then you got to figure out your central atom. This is usually the least electronegative one. So it's also never hydrogen, because remember, hydrogen only has one valence electron. It can only make one bond, so it can't really fit in the middle. And then, least electronegative, never hydrogen. And then you start with single bonds to try to use up all of those valence electrons you counted up in step 1. If that doesn't use them all up, move to double and triple bonds. And then if that still doesn't work, then we put unpaired electrons, non-bonding electrons on atoms in the central atom. Okay, so let's start with number 1. Carbon tetrachloride. Okay, so let's look at our rules here. First, we got to count up the valence electrons. If you look at your periodic table, carbon is in the 4th column, right? So 1, 2, 3, 4. That's how many valence electrons it has. Carbon has 4 valence electrons. We do the same thing with chlorine. Each one has 7. And there are 4 chlorines, so we know there have to be 28. 7 times 4, 28 total. So we know we need 32 valence electrons. So next, let's figure out our central atom. Carbon is the least electronegative, so it is going to be in the center. Okay, so now let's start with our single bonds, right? 2, 4, and I'm going to draw it this way. Hopefully I'll explain this in a second. This is just to say, this is kind of what it looks like in 3D. So this fluorine, it's called out fluorine 1 and fluorine 2 are in the same plane, like on a sheet of paper. Then this filled in triangle means that this fluorine is sticking out into the paper, like a pencil through the paper pointing at you, and that fluorine is behind. Okay, so now we know that fluorine's got a bunch of valence unpaired electrons. Oh, sorry, I wrote fluorine instead of chlorine. I'm sorry, I didn't even realize that. Just replace that real quick. Okay, so now if we count all these up, each chlorine has 6 around it right now, okay? 6 unpaired and 2 bonding. So each has 6. 6 times 4 is 24, plus these bonding ones, which is 8. So that's 32. I just feel like it's easier to do it that way, adding up the number of non-bonding first and then the bonding, because then you can easily multiply it. Sometimes it gets funky trying to count with all of these, but that is that structure. Yes. Okay, number 2 is N3O2. Okay. So first, which is least electronegative? If we look at the periodic table, as you go right, you get more electronegative, right? So that means these nitrogens are going to be in the middle. And then the oxygens are going to be kind of like that. Okay. So now let's do a little experimenting, because that's what you got to do with these. When we add up all the valence electrons, we know nitrogen each has 5. So that'll be 10 total. Each oxygen will have 6. So that is 12. So we add these up, we need 22 valence electrons. Okay, so let's see. Let's first put some single bonds in here. Sorry about that. Okay, that takes up 2, 4, 6. And we want these charges to be balanced on either side, right? So I think we should try to put 11 on either side. So see how we have 22 total? just try to balance it. So there's 11 here and 11 here. So if we have our oxygens like that, this is just an experiment, remember. We're just trying to see how this might work. 2, 4, 6, 8, 10, 12, 14, 16, 18. We need 4 more. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Perfect. Okay, but now we have to look at formal charge, and that's the fun part. So formal charge is equal to the number of valence electrons. Valence. I don't know why it's not letting me write there. Number of valence minus 1/2 the bonding electrons minus non-bonding. It's just more of a concept than an actual number. So if we look at this for oxygen, our formal charge is going to be the number of valence electrons it has with this, which is 6, minus, it has 2 bonding electrons, right? Like 1, 2, right? Technically those 2 are there. So we're just going to subtract 1. Here, let me just write this out. Like that. These represent 2, right? That dash represents 2. And subtract 6, we get -1. It's going to be the same thing for this oxygen here. Okay, how about this nitrogen? Formal charge is going to be 5 minus the number bonding is 4 minus non-bonding is 2. 1, 2. So that's going to be 5 minus 2 minus 2 plus 1 plus 1. Okay, our goal is always to minimize formal charge. We want to avoid it completely if possible. So this isn't too bad because we always want the most negative charge on the most electronegative atom, which is happening right now. That most electronegative atom is the oxygen. So this isn't bad, but let's see if we can improve this. Okay, so we know that nitrogen has a +1. What if we stick one more bond in there? Because in here, it's important to realize that nitrogen doesn't even have a complete octet the way I've drawn it. So if we draw it this way, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Let's see that. 2, 4, 6, 8, 10, 12, 14, 16. I made a little mistake there. I think I gave oxygen too many. Okay. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, let's look at this one. So each of these has an octet, which is really important. I should have written that here. To give octet. That's really, really important. I don't know how I forgot that. See, octet. Each of these wants 8 electrons. Wants 8. So that's our goal. Okay, so now if we look at this, formal charge is going to be 6 minus 2 minus 4. So that's 0. Perfect. 6 minus 2 minus 4 is 0. Now on our nitrogens, 5 minus the number of bonding is 6. Divide that by 2. 3 minus 2 is 0. Okay, this looks like it is our structure. Okay, number 3. This is going to be a long video. I'm warning you just now. Okay, PBr3. Okay, so if we look at the periodic table and we add up the number of valence electrons, phosphorus has 5 and bromine has 7 each. So 5 plus 21 is 26. So our phosphorus is going to be in the middle. It's the least electronegative. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We need 2 more. Now what we can do, because phosphorus is in the 3rd row, is we can just stick these extra ones on phosphorus. Actually, we don't even need to worry about that. Never mind. Forget about that for a second. So all of these have 8 now. 8 valence electrons. And that looks good. Okay. 4. BI3. Okay. So boron has 5. no, boron has 1, 2, 3, sorry. 3. Iodine has 7 each, so 24 electrons. So one important thing to realize with boron is that boron sometimes has an incomplete octet, meaning that it doesn't get 8. It sometimes is just happy with 6 if that works for the molecule. So when we add these up, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, there we go. There is our structure. Now, it's important to check formal charge, but some of these you can be pretty sure that that's correct. Okay, C3H6O. Okay, this is going to be kind of a fun one. What usually happens here is that the carbons are bound to each other in a carbon chain, and then you have hydrogens sticking out like that. So, and you probably shouldn't do it this way, but this way helps me see it okay. But that doesn't quite work, because what we see here is that it's not really symmetrical, right? Like, you can't have the oxygen somewhere there, because then this one doesn't have a complete octet, and one would have an expanded octet. So if we undo that, first, I can't believe I missed this. You gotta add up your valence electrons. So carbon has 4. 4 each is 12, plus 6. Hydrogen has 1 each, so that's 6 total. And oxygen has 6. 12 plus 6 plus 6 is 24. Okay, so now let's try it this way. Let's say the hydrogens are bound out here like that, right? And then the carbons bond to each other, and then the oxygen fits like that. Okay. What happens a lot with these Lewis structures is that you just have to get creative. You have to think of different ways to structure these molecules. When we add up the valence, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Perfect. Okay, moving on. Sorry I'm going so fast through these, but yeah, creativity is the number one thing. You just got to think of different ways of structuring these molecules, with formal charge being your backup, telling you when to do that. Water is an important one to know. So hydrogen each has 2 valence electrons. Oxygen has 6, so we got 8 total. So then, remember that hydrogen can never be in the center. It can never be in the center because it can only make one bond. What we see here is 2, 4, 6, 8. When we check formal charge, we get 0 here, 0 here. Oxygen is 6 minus 4 minus 2, 0. Perfect. Okay, 7. We got CH4. Now this is going to be just like the first one, CCl4. So if you start to recognize these structures like XA4, XF2, something like that, then it'll start to help you categorize these molecules and figure out how to draw them, their structures, very easily. So we got 4 here plus 4, so that's 8 valence electrons. And I'm going to draw this the quote-unquote normal way, so you can just see the difference between this and this. Helps you see the 3D aspect a little bit more. This one's just flat on the page. 2, 4, 6, 8. That's good. Okay, moving on. SO2. Okay, so sulfur has 6. Oxygen has 6. So we need 18 valence electrons. Okay. So sulfur is going to be our central atom here. It's less electronegative. So let's just try with some double bonds right now. Because if we look at this right now, we can say 8 on either side isn't going to be quite enough. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And now if we check the formal charge, we'll see that all of these, oxygen is 6 minus 4 minus 2 is 0. So that's 0, 0. Sulfur is also 6 minus 4 minus 2 is 0. And remember, for formal charge, you take like the number of lines there are, so 4. multiply that by 2, and then divide it by 2. Yeah, I hope that makes sense. I guess you could just take the number of lines there are. It's an easier way to think of it. Bonds. Okay, NH3. Nitrogen has 5 valence electrons, hydrogen has 3, so we got 8 total. Now we're going to put nitrogen in the center because hydrogen can never be in the center. And then 2, 4, 6, nitrogen needs to complete that octet. It will have 2 there. And yep, formal charge, all set. So finally, number 10, SiO4. So if we look at the periodic table, silicon has 1, 2, 3, 4 valence electrons. Oxygen has 6 each, so 24 total. Got 28 valence electrons. Okay, so silicon, oxygen, 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 oxygen. Okay, so we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I hope I can't really add that well. I think we might be over our limit here. Let's see, what can we do about that one? We might need to switch some of these into double bonds to get rid of some, quote unquote, get rid of. So when we do it this way, and this is kind of just experimenting, remember, with Lewis structures, that's kind of what it's like. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. What am I doing here? 2, 4, 6, 8, 12. Okay. I think I made a little mistake here somewhere, but yeah, this is what the structure looked like. It's tetrahedral, so it's just like that CCl4 and the CH4, with silicon in the middle and oxygen like that. I think there's some funkiness with the Lewis, with the valence I'm not seeing, but yeah, this is what the structure looks like. Okay, so I hope this helps you figure out Lewis structures. Remember, just follow these rules and then learn how to categorize these, and then you'll be doing these in no time.